welcome back. This is a shop talk number 24. As you can see, we are in a new shop. Decided that it's finally time to leave the basement and pull most of the machines ground level. Means lathe, mill, deep bit grinder, surface grinder, and some of the smaller machines are going ground level. This is part of the shop that I acquired for the CNC over there. I'm going to do a quick tour of the two rooms in a second. Next to me you can already see the MCO Super 11 already almost back in operation. Behind the camera there is the Optimum MB4 milling machine. Man, it's still in parts because it's bloody heavy. A friend helped me to move it. I have some footage of me moving. Sorry for the vertical shot video. This was done on my phone and I didn't anticipate to put it in a video, but here we are. First part was the milling machine head. Then I changed setup to lower the entire base and column and C-slide of the machine off its base. In hindsight, it's not that crazy heavy. Two strong men can lift and carry it. We took the whole base and column on a hand truck, pulled it upstairs and lifted it by hand onto the machine base itself, onto the table backup. But me doing this alone to dismantle the mill, this was a very safe option. I have my bench already up here, the table with surface plate, and I have daylight. I put in some LED lighting on the ceiling. It's super bright in here. And I removed part of the wall into the other shop. So let's take a camera and take a very quick glimpse about the mess I created here. So as you can see, this is part of the house. There's the regular house entrance door. This is also where I used to go in and down the stairs into the basement. And this is the new shop. This is an attached part of the building. This used to be storage. And there is a second door which I'm going to cover up. This is not going to be an entrance anymore. Why? In a second. As you can see, I have the MCO Super 11 lathe back here. I have my Optimum milling machine here. 400 volt, 3-phase, compressed air line going all the way around the shop. Here is a miniature model of the shop that I 3D printed. As you can see, this door here, this is where we just went in. Here's the milling machine, a tooling cart. The MCO lathe goes straight onto that wall. Bench, table with surface plate. There will be another table here with the measuring microscope. And then I took out a piece of the wall here. And over here, this is where the Deckel S1 tool and cutter grinder lives that you already know. The Sorotex CNC router, my CAD CAM place with the PC. Over here I have the deep bit grinder. And this will be a new acquisition. This is a large gear-headed Morse Taper 4 drill press, because I need a drill press at some point in my life. And the surface grinder will go back here. How this all fits together. Let's get the door closed. This is the piece of the wall that I took out. I have some construction photos that I will include here. The wall between the two rooms is cinder block with sheetrock on the other side. I left the sheetrock in place as long as possible to keep the dust contamination on the CNC side to a minimum. Here you can already see the finished wall breach with the concrete girder on top to keep the remaining cinder blocks from dropping down. This is the Bosch pneumatic hammer that I used. It's a little bit undersized, but it's still better than using a sledgehammer. Even a small wall breach like this creates an enormous amount of rubble. This is after most of the sheetrock and drywall work was done. And I'm reasonably pleased with myself how it came out. I used to do projects like these, bricklaying and construction, every time together with my dad, but since my dad isn't anymore, I have to do it myself. I have the surface plate with the cabinet. The doors are opening that way. The tooling cabinet, the tooling cart here will go away. Bench, which is a horrendous mess. 230 volt outlets here and here. Window, nice view out the window. It's slightly overcast today, but still a decent day. 33 degrees C, but super humid. Very, very tough. Today was also the day when we took these two machines and moved them upstairs. Over here, as I said, the CAD/CAM place with a PC. Here's the CNC router, which already has most of its enclosure built. It still lacks a door, a sliding door. Ladder. There is the Deckel S1 tool and cutter grinder. Always a beautiful machine. And a new acquisition. This is a Volpert hardness tester in excellent condition. A good friend dropped this off at my place. I traded it against a vibratory compactor for construction sites, and we both are very happy. It's in excellent condition. It came with a small tin of the replacement of the original color for touch-ups, a replacement indicator, hardness standards, just everything that you need to go. And I always wanted one of these. I will talk about this separately, of course. As you can see, already has eyes. He also gave a beautiful Deckel FP3 model to me, 3D printed, with eyes. And this is the breakthrough through the wall from this side. The floor needs a concrete wedge on this spot here, because the floors in these two rooms are not the same height. The big grinder is already here. There are some parts of the milling machine, construction tools. It's a horrendous mess at the moment, but I will sort it out. And here again, view into the manual side of the shop, and this over here is grinding and CNC. Yes, I know, it would be a good idea to put all the grinding machines over here and all the machining machines over here, but that doesn't work out with the layout. The grinding room would be too large and the machining room itself would be too small, so it doesn't work out. Couldn't be happier. But since this is a shop talk, I have of course some machining projects and some informational topics too. So let's get started with these. This is another project I'm working on. I'm sick and tired of hand cranking the table of the surface grinder back and forth by hand. So I decided to get a robotic slave down here to do this for me. This is a JLC closed loop stepper motor, 3 Newton meter with integrated driver, and this is cranking via a 85 toothed belt directly on the table drive of this grinder, which is a rack and pinion drive in here, and it works excellent. So I need to bore 10 of these gears. These are module 0.4 gears, 45 teeth, 4mm thick, made from brass. This is an aftermarket part. I ordered these from a small manufacturer in Poland, which did a beautiful job on hobbing these. And I need to bore them to 10mm. And I had a few options to do them. I could bore soft jaws on the lathe chuck, or bore an emergency collet to size, or make a small fixture. I decided on a fixture because I didn't have a spare emergency collet, and also I'm not the biggest fan of holding such a delicate gear on the OD of the teeth. This fixture has a locating diameter here where the gear goes in with about 10 microns of looseness, and has a cover that goes on top of it and holds it in place axially. So I don't distort the OD, but it's located and held in place for machining. And this fixture was turned, I machined it, drilled it, then I put it in the chuck, and while in the chuck I bored this recess for the gear, and also face the bottom, so it's running very true. It's basically running as true as the bearings in the spindle of this machine. Of course, a hopped gear, you have to check that the real OD of the gear runs true to the pitch circle diameter of the gear. In some cases, if somebody did sloppy work, that's not the case. You can check that on the surface plate with a small gauge pin between the teeth. Then you can check the run out of the pitch circle diameter. The gears go in like this. Then you get this cover here on top. It's not the crazy fastest fixture. I only have to do like 20 of these parts, so it goes fairly quick that way. If I had to do more, I would do elongated slits in here, like keyhole slits, so I can remove the cover without unscrewing the screws completely. Semi-tightening the screws. Then I have a torque wrench here, 1.2 Newton meters. And I torque down the screws to an equal amount. I bought these wrenches for my inserted tooling, so I don't over tighten and strip the insert screws or break an insert in case of the very small ones. These cost like, I think, 15 euros a piece. They are not adjustable. They have one torque setting, and that's what they're used for. But they're also very useful for small fixtures. This is the boring bar I'm using. This is a small solid carbide boring bar by Göring. Very good condition, very, very positive cutting action, excellent quality. Could do the same work with a high-speed steel boring tool or a shop ground tool too. But I still had this boring bar from a different operation, from a different job, and so that's what I'm using. The gears already have a 1.5 millimeter center hole, and as this is brass, we can take a fairly heavy cut for such a small boring bar. We can go right away from 1.5 to 5 millimeters in one pass. Second pass from 5 to 8. Third pass to 9.9 millimeters. And last pass to 10.01. So checking the ID with the tri-mic, here we go, that's 10.01, pretty much spot on. Center of tolerance, that is. Go, no-go gauge. This side is nominal diameter +0, and the other side is +15. So this goes, and this side doesn't. Let's get the part out of the fixture. These torque wrenches have only a tightening torque. For loosening, they have so much torque until they break. Take 2 screws of the fixture out, loosen this a little bit more. I'm using the bit alone because it's a little bit speedier than the large wrench. Here's another part that goes along with the brass gears. This is a bushing machine out of the same alloy of brass, free machine brass, and it's turned in one setup. Now I'm parting it off, almost. When I do a part off operation on something like this, I always take like a roughing pass, and then I do a finishing pass on the face with the same parting tool. Take a file, deburr the back side. Then I part it off completely, holding it with a small pin not to drop it in a chip pan. And that way I get a part that's finished on the back side, except for a chamfer on the through hole. I'm soldering the parts together on a hot plate using low melt temperature silver solder, and I just put the flux on both parts, put them together, and add a tiny piece of the silver solder and heat it up to about 350 degrees C. Here we can see the silver solder joint after cleaning off the flux, and here are all the finished gears. The method of putting them together from two individual parts was still faster and cheaper than machining the complete gears from scratch. Okay, one could say that I have a slight obsession with die grinders, handheld, high-speed grinders. They're just a very utilitarian tool that I use constantly for deburring, cut-off, sculpting, engraving, manual engraving, just for everything. Blending surfaces, polishing, you name it. I started, this thing is now probably 20 years old. This is a made in Germany Proxxon Minimot 40. This is a 12 volt hobby grade, high-end hobby grade die grinder basically. It turns only 20,000 RPM, but it's well made. It's better made than most Dremels. It has actually nice steel collets, slit 3 times, ground and hardened, compared to the die cast collets that Dremel uses. These are fairly affordable. I think the set with the power unit, this has a transformer unit going along with it, was about 75 Deutsche Mark. So that's today probably about 75 euros. So this served me very well. I used it a ton. I still use it to this day, but it's getting long in the tooth. So this was my first one. I have a large electric die grinder. I have a pneumatic right angle die grinder, but those are more for rough work. So next one I got was the Biax SRD 3-55-2, which is 55,000 RPM air-powered die grinder. That's the same die grinder I have at work, at my bench, and I really like it. It's a great little die grinder. It has just enough power to be really useful. The 55,000 RPM are really nice for carbide burrs. You can really hog off some material with these guys. And the nice thing about them is it's tiny compared to the Proxxon. This has more power, more speed, and is smaller. They can be rebuilt. They have an air motor in them with phenolic vanes. Those are available for rebuilding those. You can get the bearing set for the front here. So they're really not hard to rebuild. My former, now retired foreman, showed me how to rebuild them. It's really not a big deal. You unscrew them, you pull everything out, and then you just replace the parts. Simple. And they're stupid loud. They're really loud. Almost annoying. My coworkers really like when I use it. And another very good aspect to them is you don't need a power pack for them. You don't need a transformer. You just hook them up to air and you're ready to go. And especially at my day job, when we're out on the shop floor working on an installed machine and we have to modify, for example, just a bolt hole pattern, and you can't take the part to a machine. You take this to the machine with a carbide, and you just chew away at it and use this to make it work. Very handy, very mobile setup, and that's what I'm going to use it still at home, even if I have an alternative now. So I really like the air-powered die grinder, super versatile tool, kind of kind of affordable. New, these are like 600 euros, but they show up on the used mark all the time, and they, as I said, they can be rebuilt. Personally, I would stay away from the cheapos for like 20 bucks on eBay. I had one of those for closer inspection, means took it apart, and no offense, but they are a heap of crap. They are poorly made. The run out on the color check is stupid. The die cast insides and the air channels are just rough and not deburred. Just not well made. They take even more air than these. They're louder, have less power. Just not ideal. They need air with oil in them. And at my bench I run them off an oiler, but when we use them out in the field and at my day job, we just occasionally drop in a little bit of oil into the air hose, and we have die grinders that are basically older than me. Same style, same Biax 55,000 RPM grinds, and yeah, you can't kill them. Very hard to kill them. And then there are these things. This is an NSK Emax Evolution micromotor die grind. Full disclosure, this is expensive. This is almost stupid expensive. The motor, that's a modular system. You have a motor and you have a head. You can take the head off, it unscrews with a spanner wrench off here. You can take it off and you can put out other attachments on. The motor goes to a power unit. That's a power unit. It shows the RPM here. This large jog wheel sets the speed from 1,000 to 40,000 RPM. You have start and you have reverse, and you can hook up a second motor, for example a filing machine or a second grinder. But why are these so expensive? Well, they are made in Japan, which is usually already a sign of a rather expensive item. They're super well made. This is a brushless motor. The spindle runs very true, below 10 microns, close to the collet. And this head I got here is a quick change. So you just twist it, take the tool out and change it, and you twist it back and you're ready to go. I have a 3mm collet in here. You can just spin this out and put this in. This is a 2.35mm collet. This head goes up to 1/8 inch. There is also, you can get a speed reducer head, which is a 1:4 reduction speed, and mount, for example, a 6mm heavy duty head on it. It takes 6mm tooling, so which would make this thing in a fairly heavy duty die grinder or polishing machine. There are right angle heads, 45-degree heads, a really tiny, slim right angle head that go into a bore as small as 13mm in diameter for deburring cross holes. You can get a filing head, two different styles of filing head. One is going back and forth, and the other one is going side to side, which is really nice. If you have to work up to a shoulder or a vertical wall, you can work a surface like this up to a wall next to it. There are different styles of collet, spindle heads. This one is a quick change style. There's with the twist lock. There is a lever lock style. You can also get the classic ones with 2 wrenches if you desire. It's just a nice system. And another reason why they are so expensive, let's dial in 20,000 RPM and start it. So that's 20,000 RPM, and I did not modify the audio volume of this video. It's fairly quiet. Let's drop it down to, let's say, 5,000, which you might use, for example, for polishing with a buffing wheel, or using a Cratex wheel or something like that. 25,000 RPM, which you would use for maybe a small cutoff wheel to cut off a hardened pin. Or you go all the way up to 40,000 RPM. It gets a little bit louder, of course. It's 40,000 RPM, but it's far from being very loud. And 40,000 RPM is of course very good speed for carbide burrs. I like the third carbide burrs, like this one. This is a single cut, fine tooth profile, which works excellent for chamfering materials. When you deburr, or chamfer, you usually want to go climb cutting. It's very controllable that way. So, as you can see, super smooth running. Even freehanding a chamfer this way is a very quick way to get a clean chamfer compared to filing. That's one of my most used deburr tools at work, the Biax die grinder. We're doing a lot of Lexan, and I can't stand these. They are just annoying. I prefer to run a die grinder over the edge of a cut piece of Lexan, or I'll put a nice little chamfer on it. So yeah, that's I'm not entirely sure this section was any useful for it, except for showing off a new tool, but dang, is this a nice tool. So it's just a beautiful tool. Yes, it's crazy expensive, and for a lot of people it might not worth it because they don't use die grinder that much. I live and die off a die grinder in the shop. Very important tool for me. One nice thing about having two vices on the table of the mill is that you can hold a lot of work holding devices in them without having to remove them and strap clamping or bolting them directly to the mill table. In this case, I'm holding my small vacuum chuck directly in the two vices, supported by parallels, so it's good and level, just to surface some Delrin blocks. I need these to be about 10mm thickness, and the Delrin comes as an extruded plate and is usually oversized. So I have to take off 0.3mm on each side, and the vacuum chuck is the easiest way to get such a plate nice and parallel. Not straight, just parallel. There is a distinctive difference between those two terms. This is just a standard grid pattern vacuum table. These are great for work where you do not cut through the material. The hole pattern vacuum chucks are great when you want to cut through your material. These lose holding power immediately. And I don't have a vacuum pump. I'm running a Venturi valve. This thing here, this creates vacuum and noise from compressed air. So this is the vacuum connector. This goes to the vacuum chuck, and this ball valve turns it on. All the exhaust air goes out through the silencer here, but it's still loud enough to be annoying as hell. And that's the reason why I barely use it. But sometimes it's a very good option. So this type of work holding with a vacuum chuck gets you a very parallel workpiece, because if the material you put on it has a little bit of bend or bow to it, it will usually flatten it out, just like on the magnet of a surface grinder. If the part is bent and you put it on here and turn on the magnet, or in this case the magnetic chuck, it will suck it flat down on the chuck. And you have no way to get that bend out if there is one. You can try to shim it somehow off under the bow, but that's a nightmare. There are better ways to do that. But in my case, this material is already pretty flattish, good enough for this case. And I just needed 10mm thick. So I already cleaned up one side using this 4 insert, round insert face mill, running at 1000 RPM, 400mm per minute feed, and a depth of cut of 0.3mm. The part hangs over a little bit, but it is what it is. So when I turn on the Venturi valve, you will see that this gap here closes and the work gets pulled flat against the face of the chuck. Okay, there we go. That's one plate down to 10 millimeters. 1002, 1001, 1010 right on. So that's pretty good for plastic. And here we have some footage of a very wide plunge cut in some commercial heat-treated steel that comes in at around 40 Rockwell C. The trick with wide plunge cuts is super rigid mounting, solid tool posts, good work holding, in this case 6-jaw chuck, a cutting edge that has been lapped to perfect condition, some good cutting oil. I like the Yokish Alpha 93 cutting oil, and then you just take a plunge. You just peel off the material. Look at the beautiful chip curling off the cutting edge at almost full width. And if the setup is rigid enough, you can even take a very light cut and really peel off the material very controlled. That's the beauty of a very sharp tool. And the finish is marvelous. I had to modify some set scale miniature train model bodies. These are die cast zinc, and the customer supplied this very practical wooden fixture with 2 strap clamps and Phillips headed screws to hold the already painted bodies without damaging them. And I just had to take off some material off the top of the body to lower the roof, because in original condition these bodies were not exactly to scale. So we lowered these a little bit using a 2mm 2-flute carbide amp mill and going very careful at it. It would be rather disastrous if I damaged one of these. I had to do about 100 of these train engines or train engine bodies, and I didn't damage one. But when you work on a finished painted model, you have to be crazy careful. The cycle time was fairly quick, and the fixture was also very quick to load and unload without too much hassle. The same train engine bodies also needed a second operation, this time on the inside. And again, the customer supplied a wooden fixture so I can clamp them in a vise, which worked exceptionally well. The body goes in the wooden fixture in the vise and then just pushed up against the magnet on the side of the vise as a stop. And in this case we just need to mill out the inside to make room for a new motor. Again with the same 2mm 2-flute carbide end mill, and I'm taking fairly light cuts not to damage anything substantially inside or outside of the body. And yes, I'm cutting a whole lot of air here, but I preferred to do a pocketing routine that thinks there is material instead of wrapping into some material that might be there or might not be there. So that brought the cycle time up to something like 2.5 to 3 minutes, which is still acceptable for this work. The customer supplied the train engine bodies in 2 boxes like these, sorted and numbered through, which made it very easy for me to keep track of everything. Here I'm working on a fairly complex brass part that needs 3 pockets and other features indexed on its outer diameter. And instead of using a indexing head, I decided to use features that are already in the part for indexing. The one face of the part has a bolt hole pattern with 6mm precision bores, and I can use some end mill shanks in these bores to index the part. The part rests on a set of parallels in the vise, and the indexing is done by the two tooling blocks and some gauge blocks to get the two pins level. The X direction is taken care of by a magnetic stop on the side of the vise. So now that I know that the end mills are nicely resting on the gauge block, I know that I indexed my part properly and I can do my machining. This is all CAM work, it's all done in CAM. No programming on the machine in this case. So I didn't show much machining of this part. In fact, I didn't show any apart from CNC cutting those pockets, because these parts were just hugely complicated, or in fact this one was hugely complicated, and I wanted to concentrate on the part and not have to deal with filming it and machining rather complicated part. But the point that I wanted to bring across is that you can use features on a part for indexing the part itself. In this case, these 3 precision holes were essential in my machining process because I could put in some carbide pins and use them to index the part on the CNC mill. I already had planned to put the manual Walter indexing head on the CNC router, but this setup was way faster and just as accurate as I was indexing off the features directly. And the way this all goes together, we have this little part. This is stainless, 304, I think. This drops in here. As far as I can tell by the drawing, there is a Bowden cable going in from the back, attaching to this piece here. Then we have this retaining plate, which drops on top, a little bit proud, bolts in with 4 M2 screws. Then we have this cross hole here. Then once these are finished, these drop in here, get pinned in place, and via a linkage that not I am machining, which connects from this slider down there into this pocket here. This allows this wing to open up and close when this moves. And you have 3 of these around the circumference of the part. And yeah, that's the assembly. Thank you all for watching. I hope you found this somewhat interesting, even if it's mostly talking me about the new shop, which doesn't do much good for you, but you get an idea why things are happening so slow at the moment. Thank you all for watching. Thanks for the ongoing support, and I'll be back. A good friend mentioned that everything I do should be underlaid with my intro and outro music.